Thanks for having me here today. My name is Ning Shi. I work in the engineering department at Klaviyo. By the way, the company is pronounced Klaviyo, Klaviyo or Klaviyo, where most of the people don't know how to pronounce the company name. So probably most of you haven't heard of this company and wonder, what Klaviyo does. So I want to give you a brief overview of what Klaviyo does. Klaviyo is an e-commerce platform that helps e-commerce businesses grow. And the way we do that is mainly through three different types of things. First, we process a lot of real-time analytics on consumer events. And we also have event-triggered actions based on analytics. Last but not least, the bread and butter of Klaviyo is best-in-class email marketing. And by saying events and all those like consumer events and analytics, what do I mean by that? So here's an example. To your right, you can see a very simple email open event, meaning that person identified by John at example.com opened an email message with the ID ABCDE at that timestamp with that IP address. And John happened to be using a Safari version 12.0.1. So that becomes an event that gets ingested into Klaviyo, and we process that event to generate analytics for our customers to see. And our customers are those e-commerce businesses, so they can go onto Klaviyo, look at what's happening about their business, how their business is trending, and gain insights into how the business is doing. Hopefully, with these knowledge and information, they can improve their business and increase the revenue. So with that simple event, I turned that into a table format so that it's easier for you to read. It's basically broken down into different dimensions. You can see the first dimension is the email provider, which is example.com, and the message ID is ABCDE, and the campaign name is holiday sale, and such, and then lastly is the browser type and version. So that's how a single event is represented within the event processing pipeline at Klaviyo. Why do we do this? With thousands of types of events that we process every day, we handle close to 100,000 events per second during peak times. So this number may not look big to some of you, as we were hearing in other talks. Typically, they're like in the millions, or sometimes it's billions of seconds per second range. This is like, comparatively speaking, this is a small number. But I'll explain later why this is posing technical challenges for us. But by doing the real-time analytics, the type of questions that we can answer for our customers is things like this. How many unique individuals open emails from this campaign between 3 a.m. and 4 a.m.? Or another question that you can ask on Klaviyo is, how many unique individuals purchased at least 2 black iPhone chargers after reading this campaign email yesterday? As you can see, these are pretty deep analytics questions, and it involves not just one type of event, but many different types of events through a period of time. We have to connect the dots together, and then we are able to answer questions like this. Specifically, the technical challenges I was talking about is from 2 different aspects. First is that we have so many user profiles. These are consumer user profiles, over 1 billion of those. That just makes the dataset size really big in terms of cardinality. By saying cardinality, I mean distinct values. So each individual user profile is an individual value. So with over 1 billion user profiles, whatever you're tracking, whatever you're doing, you end up having to track for more than 1 billion user profiles doing that at the same time. And the other aspect is that we have a large state that we want to track at real time, mainly for duplicate detection. And here, the duplicates are a little bit different than just the same message repeating itself in the Kafka message queue. For us, duplicate means that the same profile or consumer doing the same action multiple times throughout the day or throughout the month, and we want to count the number of unique times this user has done such an action, not the number of times repeatedly. So for example, when you receive an email, you might open that email multiple times throughout the day, or either intentionally or by accident. So what we are interested in, what our customers are interested in, is how many unique users actually opened that email, not that how many times each person opened that email. So in order to track the unique count of open events, we need to be able to detect duplicate open events. So those events will come into Klaviyo as different or distinct events, but if they are the same open events for the same person, then we have to deduplicate that. And the other aspect is that we have a very high fan-out ratio. As we've seen on the previous slide, that's actually a very simplified version of an event. Usually when an event comes in, it's more complicated than that, and we hydrate that with a lot more information so that when we actually blow it up into different dimensions, we typically end up having 200 to 300 different dimensions for a single event. So the fan-out ratio is usually 1 to hundreds. And with both of these, high cardinality and the high fan-out ratio, what we end up having is we have to track and update millions of metrics at every second. That's why it's a challenging workload for Klaviyo. And this is a high-level overview of what the event processing pipeline looks like. So when events comes in, we save it in a single source of truth so that we can either replay or do repair afterwards if needed to. But after that, we send it to 2 parallel streams. We basically tee the event to 2 different streams. One is for customer level aggregation, meaning that it's at a single profile level, how many times you've done certain action. And the other stream is at the account level, meaning that it's at a e-commerce business level. So how many different individuals have opened this email campaign message, or how many people made any purchase of this product throughout the day. So these are at the account level. Then we save the pre-aggregated results in separate Cassandra clusters. The initial version that we had for a couple of years was written in Python, custom Python code, and leveraging Redis clusters to track the events flowing into the system and doing duplicate detection that way. And we also have a separate Redis cluster for aggregation. Then eventually the aggregated results get saved into the Cassandra cluster. That had a couple of problems. First of all, because it involves so many different moving parts and it's constantly talking to external systems, failures, network connectivity issues could happen, or node failures could happen, which results in non-deterministic results. When you recover those machines, how do you know that the previous transaction or request was successfully done or not done? So sometimes it ends up with inaccurate results that way. And also, having so many different clusters to manage is kind of a painful process, because any one of the clusters could have node failures or connection issues, and you have to deal with many moving parts. So last year, we spent a lot of time and effort building this new solution based on top of Flink. Now, this is what it looks like. So events flow into Kafka, and a single topic in Kafka, and then a single Flink job will then consume the events off of Kafka and do duplication and also do real-time aggregation based on the dimensions and the timeframes that you want to aggregate on. And then the final results get saved into the Cassandra cluster. Now we've reduced so many different moving parts or systems into a single Flink job. And the benefit was these. We gain exactly once processing. We no longer have to worry about transactions flowing through part of the system and then fail on the other part, because Flink job guarantees exactly once processing. This is a really nice thing to not have to think about or have to code around. And it's easy to scale. As you all have seen or known, to scale this, you just spin up a bigger cluster, increase your parallelism, and the job will have more resource to run the logic. Last but not least, we significantly reduced the number of hardware resources that we use on EC2 by more than 90%. So this single Flink job is now drastically smaller than what you've seen on the previous slides, where multiple Redis clusters were using EC2 instances. Next, and the focus of this talk is I want to discuss the kind of lessons learned by building this single Flink job to handle high cardinality and high fan-out ratio workload. I think it's a little bit kind of unique to Klaviyo, and we had a couple of issues when we were using Flink, and I want to share the kind of lessons learned there so that you can leverage these in your own projects. It's going to be divided into two categories. The first one is logic change or code changes, and the second one is going to be related to configuration changes. First, code changes. The very first question, probably anybody, when you started using a stream processing technologies, you want to ask yourself whether you want to use processing time or event time. And a lot of talks that we've heard today focused on the event time because it's just nicer to deal with. It's intrinsic to the events. It never changes. So it's deterministic, and also it's synchronized across the cluster. So it's kind of the go-to when you start using Flink or any stream processing technology. That's what we did. But we ran into a couple of issues, which I'll describe in the next slide. On the other hand, processing time is actually the wall clock time on each task manager, so they're different from machine to machine, depends on how synchronized they are. And because they are local to that specific machine, the next time you run the same event, the time is going to be different, so it's non-deterministic. And the third characteristic of processing time is that it's different on each task manager, of course, as I described. Depends on which task manager you end up on, the time could be different. So the reason that we picked processing time over event time is that those events that I was talking about flowing to Klaviyo, we don't really control the sources. They could come from a custom API call into Klaviyo. They could come from a third-party platform that generates those events, or it could come from customers' websites, because we're tracking so many different types of events, and they're generated by tens or hundreds of different sources, sometimes even thousands of sources. We just have no control over how the timestamps are generated on the events. So we typically see events flowing to the system. They're real-time events, but they are actually off by hours. Meaning that if we are to use event time, we would have to have a allowed lateness of up to hours or even sometimes a day, which is large, and preferably the performance is going to be impacted by that. And the second reason of using processing time is that we also have a process that synchronizes historical events. When a new customer joins Klaviyo, they want to have all the events starting from that point flowing to Klaviyo, of course. However, they also want to see their historical events end up in Klaviyo so that they can do whatever analysis they want to do. So they will initiate this historical event synchronization process, which may synchronize events that dated years back. So it's because of these two reasons, we picked processing time, which works pretty good for us, so that we don't have to worry about like lateness or different partitions have very different watermarks to deal with. That's why we built this single job to handle all types of events, both real-time, historical sync, and all these like unsynchronized external source events in a single job without having to worry about the watermarks. However, it doesn't come without a cost. By using processing time, we have to be careful that the events that you end up processing would have to have deterministic results. For example, at the top where you have event 1, 2, and 3, they may arrive pretty closely together that end up in the same window. On the other hand, you could end up having the same 3 events split into 2 different windows. If you're using processing time, this could totally happen when you are replaying events or when you're recovering from a checkpoint or something like that. You have to guarantee that regardless of what, whether it's case A or B, the end result has to be deterministic. So meaning that after processing all 3 events, it has to generate the same outcome. Once you can guarantee that, then it doesn't really matter whether they end up in the same window or 2 different windows. That's one of the catches for using processing time. And because of this reason that we have so many out-of-order events, one of the team members actually suggested I name this talk Flink backward. The second thing I want to share on logic change or code changes is has to do with the high fan-out ratio. So imagine that the same event that we were seeing with different dimensions, one way to handle it in a Flink job is that once you consume this in the source, you can use a flat map to split all these different dimensions into smaller events where each event contains a single dimension. So it's very lightweight internal events, very easy to deal with, so that all the downstream operators just has to think about a single dimension when they get an event. So it's easier to code that way, easier to debug, lighter events, smaller messages. Sounds great. This is what we started with. However, the performance was actually pretty poor. The reason being that, specifically related to our workload, the fan-out ratio is so high that a single event comes in that could be turned into hundreds of internal events. So this generated sort of like, you can think of it as like artificial workload that we're generating for within the Flink cluster. So all of a sudden, even though we're not hitting the network bandwidth limit, we're hitting the network message limit that Flink can process. Remember, each network message has some overhead, even though it's small, but it has to be serialized, it has to be wrapped around by metadata and bookkeeping stuff, it has to be passed around the cluster. So when you're doing capacity planning for your Flink job, when you think about network, it's not just the bandwidth, it's also how many messages you're sending. So imagine that if you're sending 100 megabyte single message, you could probably do that with a good network. But if you divide that up into 101 megabyte messages, that's different because each message has a slight overhead. So what we've found is that when you actually have a very high fan-out ratio, it's counterintuitive to actually split them out. So because this added a lot of overhead to the internal system. So what we ended up doing is using this approach where a single event comes in, we keep it intact, we don't split anything, we just let this complex event flow through the system. The downside of this is, of course, each operator, when you're coding the logic in there, you have to be aware that you have many different dimensions that you have to aggregate on. So imagine for loops in there, and you have to. The code is going to be a little bit complicated, but the benefit is huge for us because we've reduced the number of messages that we pass around the cluster by many magnitudes. By the way, we gained about 300% performance improvement by just doing this. The last thing about code change I want to talk about is windowing. This is actually a pretty interesting topic, and I didn't find this concept described in the documentation, but it's actually in the code. So a window on a given partition inside Flink. Flink is partitioned stream, and each partition has its window managed on the local machine. That single window on a partition is called a pane. That's how you refer to a single window on a single partition. So it's always referring to a single partition. And tumbling and sliding window panes fire simultaneously. Using this example here, as you can see, this is a single window starting from T1 and ends at T2. And on partition 1, there are 3 events, event 1, 2, and 4. They all end up in the same pane called pane 1. And on partition 2, because of whatever reason, there's only one event on partition 2, which is event 3. So if pane 2 only has a single event, event 3 in there, even though there are 2 distinct partitions, the panes are actually aligned. They all start at T1 and they all end at T2. And what this means is that when the window closes, both of these panes will fire at the same time. So whatever your logic is when it fires, they will both try to do the same thing at the same time. So if you are trying to write the result to a downstream system, then both of them will try to write their results to the downstream system. This is true for both tumbling and sliding window panes, triggers, as some of the talks mentioned earlier today. The triggers actually live on the Java heap prior to Flink 1.6, and starting from 1.6, they can be managed by RocksDB, which is great because now you can have a lot of triggers and not having to worry about memory pressure and things like that. What's a little bit challenging for us is because we have such a high cardinality workload, meaning that we have so many different partitions at the same time. We end up leveraging this approach. We end up having millions of triggers firing at the same time. So thundering herd effect. When the window is open or when it's between T1 and T2, nobody writes anything. But as soon as the time hits T2, every pane fires and millions of writes floods down to the downstream system, which is not good because any database or data store would prefer not to have a thundering herd or a flood of work coming into the system. So this was a major performance bottleneck for us at the beginning when we were using tumbling window. So what we ended up doing is that we wrote our custom window, but it basically works like this. It's instead of saying every pane on every partition starts at the same time and ends at the same time, we say like a pane doesn't open until it sees the earliest event. So leveraging the same example as we've seen on the previous slide, event 1, 2, and 4 come into partition 1, so opens that pane for window 1. And however, partition 2 doesn't see anything until event 3 comes along pretty much near the end of, as it gets close to T2. So the pane 2 doesn't open until event 3 comes in. It doesn't open at T1. But both panes share the same duration, meaning that once they open, they close after a fixed amount of time. So it's similar to tumbling window. The only difference here is that they don't open at the same time. Since they don't open at the same time, they don't close at the same time. So it's kind of staggered closing and staggered trigger firing. With this, we no longer have the thundering herd effect. We have a constant flow of triggers closing across different partitions with a very much smoothed out workload for the downstream system. And it improved the windowing performance dramatically. Next category is configuration changes. And I think probably the most important one is related to the state backend. And RocksDB being the main state backend, that's what we use to store our large amount of state in Flink. Before I go into the tunings for RocksDB, I think it's worth talking about how RocksDB works in general. So RocksDB leverages a data structure called log structured merge tree. And it's optimized for writes because everything is append only. You never go back to change a value that you wrote earlier. So you're always appending to the data structure, which is a really fast operation. When writes come in, as you can see, like 3 levels. And the top level is all in memory. Second and third level or below are all on disk. So when the writes come in, it goes to the active mem table. It just appends that write to the mem table. As that table fills up, once it reaches a certain size, it's going to become a read-only mem table. And it gets moved over to the read-only mem tables part. And then a new active mem table is going to be created. Once you have accumulated enough read-only mem tables, it's going to try to flush everything in memory to disk. And the on-disk file format is called SS table. And once it's flushed, then periodically RocksDB will do compaction to compact the smaller SS tables into larger ones. And you can have many different levels of that. That's the write path. For reads, when a read comes in, it first checks the mem tables, both read-only and active mem tables, to see if that value is in any of the mem tables. If it is, then great. I can serve you the request from the mem tables because that's fast. Everything is in memory. But if the value is not in the mem tables, it will have to go to disk to load that value. And after loading that value, it's going to keep that value in the block cache, which is a typical caching mechanism, just like any other databases. So that value is going to live in the block cache until the cache is filled up, then it gets evicted. So the block cache is only used for reads. All right, with this said, let's look at some of the tunings that we've done for the RocksDB backend. We found that these 4 parameters gave us the most performance boost in RocksDB. If you've read the RocksDB performance tuning guide, you probably know there are hundreds of parameters that you can tune in RocksDB, and it's kind of challenge in itself trying to figure out what you want to tune and how to tune those. But we found that these four are the most important ones for us. So I'm going to go through each one of them. The first one, block cache size. As you've noticed, all these parameters are actually tuning how much of a memory you want to use to cache values so that you can keep as much access as possible in memory. That's the key to tuning the performance. So block cache size, of course, it limits the size of the block cache you want to use for caching reads. And typically bigger the better, of course, but that depends on how much memory you want to allocate to RocksDB. And the second thing, write buffer size, is how big you want mem tables to be before they are frozen into read-only mem tables. The third parameter, write buffer number, that is the number of the number of read-only mem tables you want to keep in memory before it starts to flush them to disk. The last one is a little bit hard to understand. I think the top three are typically described in blog posts and in other talks, but the fourth one, we don't see that much, but I found that pretty useful. And I have an example there. So previously, we were looking at multiple mem tables. So in this picture, you can see the read-only mem tables. Once you reach a certain number of them, they're going to be flushed to disk. So when it flushes, by default, the minimum write buffers to merge is actually 1, meaning that it doesn't merge any mem tables. When it flushes, it just goes in sequence, write everything in in all of those mem tables to disk as a sequence. So it's great, it's fast. However, the downside is that if your workload constantly changes a certain set of keys, meaning that you keep updating the keys, then that's not great because you're writing the same keys with stale values to disk. And that takes up space. So this parameter controls that. For example, here, we have the same key K1 in both mem tables, but one of them has an older version, version 0, with the value hello, and the other one has the latest version, version 1, with the value world. By setting the minimum write buffers to merge to 2, I'm telling RocksDB, when you flush, go merge 2 mem tables at once to a single SS table. So what it's going to do is it's going to open both mem tables and try to merge them together by picking the latest version of the same key and only write that to the SS table. So the SS table is going to end up only having the version 1 of key K1 in there, and the version 0 is going to be discarded. A very useful feature that was introduced in Flink 1.6 was the state TTL. TTL is the time to live feature. It's similar to the time to live feature in other databases or data stores like Redis, meaning that you can, when you write a key value pair into the store, you can associate a timestamp to that key to say, I want this key to be either removed or not accessible after a certain amount of time so that it can be discarded automatically. It's a great feature. We leverage it a lot for duplicate detection because imagine that we want to track the unique open events for today, then we no longer care about these events tomorrow. So we want them to be automatically discarded. And this can be managed by RocksDB. The only catch is that the expired keys are only removed on reads, meaning that they are not automatically removed unless you try to read them. That turns out to be a big catch for us. We didn't realize that at the beginning, but once we realized it's actually pretty challenging to deal with because now you have to think about how to force a read on these values in your application or in your job. Otherwise, you're going to keep accumulating all these stale or expired states in your RocksDB files. The other way to get rid of them is by taking a save point and then restoring from that save point in a new job, but that requires some downtime, so it might not be a viable option for you. In Flink 1.8, hopefully it will come out soon, they are adding 2 new features for automatically cleaning things up. The first one is continuous cleanup. Basically, that creates an iterator on the state and constantly iterate through your RocksDB state, basically forcing a read on these values so that it gets discarded. So every single iteration, it reads, let's say, 100 or 10 values so that it doesn't block your normal operation. So it does this by piecemeal, and hopefully, once in a while, it iterates through the whole state and forces everything that's expired to be removed. The other approach is to clean on RocksDB compaction. It's implemented as a compaction filter. So when RocksDB tries to compact two SS tables, it calls this filter for every single value it sees in those SS tables to see if this value should be written to the new SS table or not. The downside of this approach is that it only cleans the values on compaction. So if you have values, stale values, that's already at the highest level of RocksDB files, those files are not going to be compacted anymore. They just stay there on disk. So they won't be cleaned up. The next one I want to talk about is back pressure. Back pressure is pretty common and when you have a spike of workload. And that's typically caused by the event consumption of a single operator being slower than the event production on the upstream operator. So in this picture, you can see task 2 is kind of running slow at the moment, and task 1 tries to send more stuff than task 2 can handle. So that generates back pressure upstream to tell task 2 is basically tell task 1 to slow down a little bit because I cannot keep up with the production rate. Higher parallelism for expensive operators sometimes help. For example, in this example, if it's computationally expensive to do task 2, you can have a little bit higher parallelism in that operator so that it leverages more CPU resources. But sometimes this approach doesn't work because you don't want to shuffle the events around due to partitioning or other reasons. And the approach that we found very effective is by using rate limiting. And when you do rate limiting, you have to put it in the source, just to remember. Because if you rate limit in any of the intermediate operator, you're essentially blocking that operator. So that doesn't work great if you're using checkpointing because the alignment now takes longer. So if you're thinking about rate limiting, put it in the source. And the best approach to deal with back pressure is to avoid back pressure altogether. Just don't let it happen. Because once you hit a back pressure, everything slows down. It takes time to recover from that. So avoiding back pressure in the first place will make your job much more healthier in terms of latency and recovery time. Last I want to cover is capacity planning. So understand your job, whether it's bounded by CPU, memory, network, or all of those. Understand the workload so that you know what to tune it for. And use fewer slots than CPU cores. I think during one of the training sessions yesterday, Konstantin mentioned that using less slots per host than the CPU cores on that machine because Flink uses some CPU cores for bookkeeping. For example, networking uses a lot of CPU. RocksDB compaction runs on a separate thread that uses CPU. Serialization uses CPU. So leave some CPU cores for those operations. My rule of thumb is to start with 50% of your CPU cores for the slots per host, and then go from there. Tune it up or down, depends on the workload. And cryo serialization is very expensive. So if you're using Podio, watch out for your Podio changes because sometimes you may forget to name or create a getter or a setter or name it correctly, and that automatically falls back to the cryo serialization. You might wonder, what happened that all of a sudden introduced 90% of overhead in my job? Sometimes it's because of the serialization. And last part, when people think about slots per host, usually they're thinking about CPU, but as it turned out, if you use a lot of RocksDB, that actually affects memory more so than the CPU because RocksDB instances is per task, not per node or per instance. It's actually per task slot on that machine. So if you have a lot of operators with states in them, each one of those on each one of the slots on that machine is going to have its own RocksDB instance. And all the parameters that we just saw for tuning RocksDB, they're going to have multiples of those on a single machine. So the higher number of slots per host, the bigger the multiplier you're getting. So plan for that. Otherwise, you may run out of memory, and that's going to be a very sad moment when this process is killed. So to summarize my talk today, the number one thing is time is of the essence. Pick processing time or event time based on your workload. Really understand your workload and reduce internal events if you can, because there's some overhead in processing and transmitting those events. And spiky workload, specifically I'm talking about the windowing here, spiky workload is really bad for any downstream data stores. So try to avoid that. For tunings, understand RocksDB if you're using the RocksDB backend. It's a little bit challenging to try to understand all those parameters, but it's going to work well. So do read the performance tuning guide in RocksDB's repo. And avoid back pressure altogether. Don't try to deal with it afterwards. And do capacity planning. All right. So all of the content I've covered today is actually available as blog posts on the Klaviyo's engineering blog. We have a series of blogs talking about all those things in great detail. So please go there and read those blogs. They're a little bit long, but they cover all the stuff I talked about today. And Klaviyo is also hiring. If you're interested in Klaviyo, come talk to me or go to our website. And if you have any questions, feel free to ask. Thank you.
Any questions? Yes?
Got this one back there.
I should have stayed in the back.
Hey, so regarding staggering windows, how does that like at all screw up like the consistency of the data model on non-keyed streams that are partitioned?
What do you mean by non-keyed streams that are partitioned?
So if you have
key in a stream is partitioning the stream.
yeah, but if you have a stream that isn't, if you have a stream that's not keyed and it's just like a uniform distribution across like various task slots, actually, that question doesn't make any sense.
Yeah, I mean that's actually a good question in a way because as I described, the panes. The custom window is actually dealing with the panes across different partitions. So if you don't have partitions, then you're just going to end up having a giant pane, a global window. So there's nothing to stagger. You're aggregating all the stuff into a single pane and then writing a single value as the end result. So there's nothing to stagger there. A single window would work well for you. If you have a high number of partitions like our workload, then this approach could help because you're essentially kind of delaying certain partitions to fire and letting others to fire first. Really depends on the workload on that specific partition. So a partition with more events, they're going to fire more frequently than the other partition that doesn't have as much events occurring.
Any other questions?
Yep.
Oh, okay. Now we start questions.
So you mentioned about like being mindful of your workloads and planning ahead based on
Yep.
that. Have you encountered a situation where your workload keeps changing or getting skewed workloads constantly? And what is your recommendation on
Yes,
maybe tackling
that's actually a good question. That's part. I would think that's part of understanding your workload. So, as in Klaviyo, our workload changes depends on the hour of day. So at noon we have the peak, and then in the early morning or late evening we have kind of died down a little bit. So you have to understand how the workload changes, and usually you're tuning for the peak moment because if you can handle that, hopefully you can handle the rest of the day, right? However, as I was mentioning that to avoid back pressure altogether, there's another reason for that because once you have back pressure, sometimes the back pressure occurs on certain operators or certain partitions. Meaning that the other partitions are going to march forward, thinking there's no problem at all. So those partitions that are experiencing back pressure, they will put back pressure upstream, creating artificial skew. So when you start recovering from back pressure, all of a sudden you end up having a lot of skew across your partitions. Some are like way ahead and some are like way behind. That causes watermark issues and that causes all kinds of windowing issues. That's why avoiding back pressure in the first place is kind of my recommendation. Otherwise you're creating a workload that you don't really anticipate to handle.
Great talk. You mentioned you were tuning all those RocksDB's parameters. What Flink metrics were you tracking to see the kind of effect those tunings were having?
I see. That's a good question. When we were tuning those parameters, there were a couple of things that we were watching. The the two things that come into my mind is throughput. Of course, you are tuning for the highest throughput of the job, like as fast as it can ingest the stuff. And the second thing we were watching was disk I/O. So you probably want to watch out for IOPS, because if you're running on the cloud using EBS or any SSD, IOPS could max out. There's a hard cap there. You don't want to hit that hard cap. You want to keep it as low as possible most of the time. During peak, it's fine if it spikes up, but you want to keep that as low as possible throughout most of your operation. Normal operation shouldn't be at the peak, right? And the other one is disk bandwidth. Yeah.
Looks like your sync was Cassandra there.
Yes.
So guessing those were idempotent writes. If that's the case, do you consider using like a custom trigger that just fires at random times and then at the end of the window if there's been an update? That way the writes would be staggered throughout the window?
Yeah, that could work. The reason that we didn't use that approach was because we try to reduce the number of windows that we have, because window itself has some kind of overhead. Because to track a window, Flink creates a data structure that tracks when the window opens, how long the window should be, and all those objects are actually living on the heap. They can't be moved to the RocksDB. They're just heap objects. So in order to reduce the number of windows that we have, we move some of that operation into a flat map or in other operators, and we just manually kind of track those, leveraging the TTL feature. Combining TTL with other operators, you can actually do some kind of windowing without the overhead of the windowing, because now you can control whether you want to keep it on the heap or in RocksDB. Just a little bit more flexible. But yeah, the suggestion is good.
Thanks for the talk. So I was wondering regarding your recommendation that we should avoid back pressure. So there are situations when we have to redeploy the application and rerun like for the time that we're down. So
Sure.
In that case, naturally, we will have back pressure. So what are your recommendations of handling that problem?
Yeah, the statement of avoiding back pressure, I guess there's an assumption that you're trying to avoid the back pressure in the Flink job. Essentially you're putting the back pressure upstream in your Kafka queue, because the queue can easily handle that, right? Like just let things queue up there, but don't let the job itself, like internally, don't let the operators get back pressure, because it takes time to recover from that. So the approach that we're taking right now is to put a rate limiter at the source so that we never consume faster than the job itself can handle. So you never end up having any back pressure in the Flink job.
Are you using the Kafka throttling feature for that?
No, we're not using that. We are using the Guava rate limiter in the source. So in the source, in the deserializer, we put a rate limiter there that we can tune.
One more. I guess we have time for one more question, and then we'll need to let guys for the next session in. If you have any questions, obviously catch Ning later.
Thank you, everybody.